Okay, we're now going to go back to the Sierpinski gasket, which I hope you've all been reading about in the book, and go through very quickly the two-dimensional recursive version. I want to point out a few things about its fractalness, what makes it fractal, and also look a little bit at the code to see, one, how it's all embedded within 3 dimensions, and talk more about 3 dimensions in this lecture. Next one, but also see a few of the little things in JavaScript that lead to more efficient code that are not how you might do it in either C, C++, or Java. Okay, so let's look at this. We'll eventually be getting in the next lecture to the 3D gasket. Here we're going to focus more on the 2D gasket and get us ready for it. So, there's not much that's going to change when we go to 3D. Basically, in terms of what we do with our data, is we use vec3s and instead of vec2s, or even vec4s for homogeneous coordinates. We use, when we send a uniform vector over, we use the uniform 3 form instead of the uniform 2 form. That's all going to be in fact true. And as we've said that everything is really stored in 4 dimensions anyway. So when you put in vec2s, they're going inside of a 4-dimensional variable using the defaults for the 3rd and the 4th components. There's just a common mode of storage in OpenGL and WebGL. What we do have to worry about that's going to be different is the order in which we render things, or we're going to have to talk about hidden surface removal, which we will in the next lecture. But let's look at the Sierpinski gasket quickly and at the recursive subdivision way of doing it. So a very easy way to look at it is that we start with a single triangle, we bisect the sides, and then connect those bisectors together that form a triangle in the middle. If it's an equilateral triangle, all those 4 triangles will be the same, and we will then remove the central triangle. If you look at the final form of the random method of doing the Sierpinski gasket, and you look at it, it looks like a big triangle in which we remove the middle, then we removed the middle of the remaining triangles, and then the middle of those remaining triangles. And in fact, that's what we can do as a recursive process. So we keep repeating that. The code is very, very simple to do. And here's after, I think, 5 subdivisions. So the first one, we got these 3 big triangles here. The second one, each of those got the center removed, and then we removed the centers again. And we can go along as long as we like doing that. Now, why is this a fractal? Well, let's look at something. Let's look at the area that's filled, the black, versus the length of all of the sides that we're looking at. So let's come back here and do it. Notice that by removing things, you started with something, if these sides were 1, then the area was at 1/2 pH, and we have the starting area. Let's say it's 1. We start with an area, and then every time we do the subdivision, we're removing some of that area. So the first time, because these 4 triangles are the same, I have 3/4 of the area that I started with. Well, when I do the next recursive step, I remove even more area. So the second step, when you add it up for all the 3 triangles that I'm subdividing, I have in total 3/4 of the area that I had after the first step. So each recursive step is removing another 1/4 of the area. So if you take the limit of doing an infinite number of steps, the final object has no area at all. But on the other hand, if you look at the perimeter, let's just look at the first step. If you look at the perimeter, if these had sides at length 1, originally then the perimeter was 3. But now each of these sides have length 1/2. So now this one has, each of these 3 corner ones has length 1/2, 1/2, 1/2, 3 halves. I've got 3 of those, so I have a length of 9 halves, which is bigger than the area that I originally, the perimeter that I originally started with. So you have this weird situation where at every stage what you're doing is you're decreasing the area, but you're increasing the total perimeter. And that's, so the perimeter is going to infinity, the area of the object's going to 0, and that can't be an ordinary geometric object. And if I ask you, well, what's the dimension of that object? Well, it's certainly not three-dimensional because the area is going to 0. Is it two-dimensional? Well, it's a little weird. So this is an example of a fractional dimension object. It has an area between 2 and 3, and it's called a fractal. And this was what Mandelbrot did. He invented fractal geometry, and gives us a way that we'll talk about later in the course of actually saying what's the fractal dimension of this particular object. But for now, we can just see it's a kind of a neat construction, and it creates something that's not within ordinary geometry. And later, we'll also see uses of fractal geometry aside from creating these kind of beautiful, interesting objects. Now let's go and look at the program for that. It's the HTML file, as we've said, will always be the same. For this, we can use a very simple pass-through vertex shader. We can rig the locations of the vertices so we don't have to do any transformation of units. The fragment shader can just set the color to whatever we want it to be for the fragments that exist. And so the HTML file is fairly straightforward. The JavaScript file is a little more interesting. So let's suppose here's the number of times to divide. We want to divide, say 5. Here's the initial triangle given as the vertices given as using mv.js to use this type. And now we're going to have a divide triangle routine that's going to take 3 vertices in, and what it's going to do is then take the number of times to subdivide. So what's that function do? Well, it either does the bisection or removes the middle and recursively calls itself to subdivide one less time, or if it's down at the end where the number of times to subdivide is 0, it's going to simply render that triangle. So let's look at those parts. Here's the little part that displays one triangle. Now this is a little bit, looks simple, but there's a couple of points here that are worth discussing. Now, when I want to render something, remember this is retain mode graphics. I've got to do it in 2 steps. I form an array, and then I put that array onto the GPU where I can now issue a render command to go and render it. So what I'm doing here in this derivation of the Sierpinski gasket is I'm actually forming an array and putting 3 points into that array. So whenever I get down to no more steps to recurse, what I'm going to do is take the 3 vertices and put them into an array. Now, how am I putting them in an array? One way, and this is sort of if you compare the code to the C, C++, Java way of doing it, you keep track of how many elements are already in the array, and then you put 3 more in there, and you either malloc array, or you know how many levels you're going to go and just have a big array. Here's a much more interesting way in JavaScript. You use the push. Remember, everything is an object in JavaScript, and objects have methods that they inherit from the prototype object, and one of which is push. So all I have to do here is push those 3 points onto the array that I've created. So I create an array of no size, and I just keep pushing things onto that array, which is incredibly simple to do. So here's where I go back a step. Here's where I created that array as an empty array. It has since it's a JavaScript array, it has a push method associated with it. I just push those 3 points on. So not only is the code clearer, it's also a lot more efficient because since it's an interpreted language, the shorter your strings are that describe the program, the better off you'll be. But I much more like the idea that this is a very simple thing. We get rid of a lot of loops by using pushes and pops and other JavaScript methods that come along with the array. Okay, now here's the rest of the subdivision program, which says, okay, I give it 3 vertices, how many times I want to subdivide. As I said, if it's the end, and here's the equal, it's exactly 0. I'm going to push those 3 vertices onto the stack. Otherwise, I'm going to create the bisectors. The bisectors use this mix function. Mix just gives me a linear combination of A and B, where it gives me this factor here times A plus 1 minus the factor times B. So eventually it's giving me sort of this going along this convex line between A and B. So we use the mix function to do that. So this is really just giving me the point halfway between A and B, the point halfway between A and C, and the point halfway between B and C. Create new variables. Now I do triangle subdivision on the 3 triangles. Each one is associated with a vertex. So the top triangle, if that had vertex A, the 2 bisectors are AB and AC. I draw that triangle, and now I do, oh, this should be, excuse me, a little mistake here. This is obviously count minus 1 here instead of count. Now let's go look at init real quickly. The init again is pretty much the same as it's been before. Here's the program calling the 2 vertex in the fragment shader that are inside. These are the IDs assigned inside of the HTML file. Here's the program object I've created. I say I want to use that program. I create a buffer to put the points into. I then send the points out to that buffer using the flatten function to convert from a JavaScript array to simply a string of floats. Then I set up a vertex attribute pointer. I enable it. This is what we've done before. And finally, I render. I mean, this is essentially the whole program right here. And then my render is simply to clear the color buffer and to draw the triangles that I've created, starting at the first one. And now, instead of adding up how many I put in there, I can use the length method to say go up until you use all of those vertices, but through points dot length. So it becomes a much cleaner, simpler function. So that's the 2D version. In the next lecture, we'll see what do we have to change to go to 3D.